Hey guys, so here we go with lecture video number 3 for chapter 6 here. One of the first concepts we're going to talk about today is percent composition. And this is in a couple of the slides that we see even after this one too, will all kind of have a lot to do with the more recent lab we're covering today, or throughout this cycle rather, not today, but on our copper sulfate hydrate analysis lab. That's kind of be almost in conjunction with this material here. So percent composition, it expresses the relative amount or mass particularly of each element in a compound. It's also sometimes just referred to as percent by mass, as well as percent composition. In the general equation here is essentially part over whole times 100, right? And that's going to allow it to convert into a percentage here. So that's kind of the main gist here, guys, right? It's the part of something divided by the whole thing, right? And we're talking in terms of mass here, right? So the mass of part of this substance divided by the mass of the whole thing times 100 is going to get you the general percentage of the composition of that part, right? So for example, if you're looking for the part of element A, when the whole thing consists of element A and B, you're going to divide element A's mass by element AB, or compound AB's total mass, multiplied by 100 to convert it into a percentage. Now, what the actual percent composition formula ends up being, first and foremost, is on table T in your reference tables, which is great. But second is this whole formula here, right? So percent comp equals mass of the part divided by mass of the whole times 100, right? So that's the actual formula that you will see genuinely on table T, and you will always have reference to, as you guys know, in your reference table. So that's great. Now, a lot of the basis for this current lab we're on in this cycle here is the copper sulfate hydrate analysis lab, right? Now that word hydrate is a little bit of a newer one, but it honestly is what it sounds like, right? Whenever you guys think about, hydrating, right? You're drinking water, you're drinking liquids to hydrate yourself. In a way, that's kind of the same thing that hydrates are. A hydrate is a compound that has a specific number of water molecules bound and literally bonded to the atoms. It includes itself as the formula unit, right? So it's followed by a dot indicating the number of water molecules attached to that particular compound. And the waters are named using our prefix system with the hydrate ending there, right? So for example, the substance that you guys are working with or have already worked with at this point in lab is called CuSO4 5H2O, which the name of that will literally translate then in English to copper sulfate, CuSO4. And then since it's 5H2O, that 5 is going to dictate the pentahydrate, right? So that prefix system that we learned about back in chapter 10, guys, that is currently on your reference tables at the very, very, very last page there, table number, I believe, 2. Your covalent prefix system, that's going to kind of come back to aid you in naming these hydrates, right? So that word hydrate is going to have a prefix from table 2 on page 13 in your reference table. In this case, since there are 5 of them, we're going to have a pentahydrate, right? 5 being pentahydrate. So that is what a hydrate is. So these water molecules are quite literally bound to or bonded to the actual copper molecules here, right? So the waters, these H2O, are bonded to this whole CuSO4 compound here. Now you might be thinking to yourself, well, doesn't that make it a liquid if water is involved? Actually, technically not, right? It's pretty cool. And again, for those that have seen the lab, let me actually go grab the substance. Okay, this is what it ends up looking like here, guys. So it's this blue-looking powder, and it's quite literally a powder. There's no There's no water in here at all. It's just a very, very cool-looking blue powder here. And again, those that have done their lab have obviously seen that and utilized it already. But what you end up doing is, as you start to essentially heat this substance up, this copper sulfate, right? Think about when you heat things up. If you want to boil off water, right, in a pot of water to make some pasta or rice, for example, guys, and you boil it, what happens is you're essentially going to force that water to boil off, become a gas, and the mass that's left over of that water in the pot is going to essentially reduce. That's essentially what happens with hydrates, right? If we heat this stuff up right here, guys, it's going to lose that H2O, that water, those water molecules that are literally bound to the powder, this copper sulfate powder in this beaker here, right? It's going to lose mass as you heat it up, right? Because that water is going to escape, right? It's going to dehydrate essentially, right? And what ends up happening is, as the water molecules start to escape, these H2O molecules escape the copper sulfate binding, this substance will transition from a hydrate to an anhydrate, anhydrate, right? That prefix of an is going to represent almost like an antihydrate or a non-hydrate, okay? Now here is kind of the breakdown of the lab techniques that are involved with this particular lab in general. You take the mass of the hydrated salt, in this case the salt is CuSO4. You're going to heat the hydrate in a crucible to drive off the water as water vapor. When the mass of the hydrate no longer changes, all water has been removed essentially, right? So all those water molecules that are bonded, rather to the substance, right, in question here, being copper sulfate, that's essentially going to represent that there's no more water molecules here, right? And when that is the case, you have this now dehydrated or anhydrate salt here. Take the mass of that hydrated or that dehydrated salt. And then lastly, you're going to calculate the percent by mass of water to determine the amount of water and the formula of the hydrate itself, right? That's kind of the rundown of this lab in particular, okay? Now, here are two concepts that we touched on at the end of chapter 10 that I mentioned a while ago that we will be circling back to, and here we are, circling back to it, right? Two concepts known as the empirical and molecular formulas. Now, we touched on it, like I said, back in chapter 10, but we're going to do a little bit more with them, obviously, specifically in class when we do some example problems. But I just want to give you a quick rundown of these two concepts once again. An empirical formula, guys, is a chemical formula representing the simplest ratio of atoms in a compound. The simplest ratio, right? So we're not talking any kind of ratio where there's an unsimplified, right, or the actual ratio. The actual ratio, or this unsimplified version, is known as this molecular formula, right, which is the second number or the second concept on this page here. It's when you've got a chemical formula representing the actual ratio of atoms in a compound. And again, there's a very, very, very stark difference between molecular formulas and empirical formulas. They both have their uses. They both kind of work hand in hand with each other. And we'll see when we get in class together to talk about and discuss these two concepts. We'll do some sample problems on how to convert from molecular to empirical and empirical to molecular. And I know to a degree we already kind of did this a little bit when we first discuss these concepts here, but we'll do a little bit more with them in class when I see you next, okay? Here are the 4 steps. They're 4 very, very basic and easy steps. And again, we're going to talk more about these in class when I see you next. That's it. Quick video for the day today, guys. That was it for the end of chapter 6, lecture video number 3. Thanks a lot, and I'll see you in class.